Alright, the last thing they want us to do in 6.4 is to solve exponential functions and then maybe some polynomial functions that may be hidden and try to be disguised as exponential functions. One thing that would be kind of helpful is knowing powers of 2s and 3s and 4s and 5s and 6. So I've written out some of the powers of 2s and 3s, and when we're solving exponential equations, kind of the first thing we're going to do is try to get the same base, and then once we get the same base, we might have to simplify the exponents a little bit, and then we'll equate the exponents. And since exponential equations are going to be one-to-one, if the outputs are equal, then they have to come from the same input. So we're going to use that property of exponential equations. Since they're one-to-one, if they have the same output, they had to come from the same input. Alright, so let's go ahead and do an example. So we want to solve 2 to the 5 minus x equals 8. So one thing to be careful of is make sure you understand that the 5 minus x is in the exponent. It's not 2 times the quantity 5 minus x. So you got to be careful there. And we want to somehow get the bases to look the same. So lucky for us, 8 is 2 cubed. So we're going to go ahead and replace. Okay. So we have outputs of 2 minus 5x and 2 cubed. So the outputs are equal. That means because it's a one-to-one function that the inputs had to be the same. So we can go ahead and equate the inputs. So 5 minus x is equal to 3. Alright, now we're going to solve this. So we're going to solve for x. We're going to subtract 5 from both sides. And then we are going to divide by -1. And we get x is equal to 2. So notice how we were solving for an exponent there. So when we're solving for an exponent, we want to get the bases to look the same, and then we can equate the exponents. Now this next example, we got to be careful of what we're solving for. Okay. All right. So notice what we're solving for. We're solving for, we didn't specifically say, but we're solving for the b. And the b is a base here. So this is different. This is like some sort of polynomial or rational equation. So the method we're going to use is going to be a little bit different. We're still probably would like to rewrite the 81, and we can rewrite 81 as 3 to the 4th, so that we would have the power, a 4th power here matching a 4th power here. Granted, that one over there is -1, but that's or -4, but we can handle that. All right, so we'll rewrite, and b to the -4 is 1 over b to the 4th, so that's looking good. All right, so 81 is 1 over 3 to the 4th. b to the -4 is 1 over b to the 4th. Okay. All right, now this 4th power function is not one-to-one, so it has a potential of giving us 2 answers. So this is a 4th power. So what we could do is, if you wanted to, you could cross multiply, and you'd have b to the 4th equals 3 to the 4th. So this looks a lot more like a polynomial function. And what's going to undo a 4th power would be a 4th root. And remember, when we take even roots, you can't forget that plus and minus. 4th power and 4th root are going to cancel. And we should get b is plus or minus 3. So we do get 2 different answers for the base. There's 2 different possibilities for that base there. Alright, let's move on. Okay, 3 over 4 raised to the x power equals 27 over 64. We're solving for the x, and the x is in the exponent. So we're going to use the fact that exponential functions are 1 to 1. However, I need to rewrite 27 over 64 somehow. So lucky for us, 27 is going to be 3 cubed, and 64 is going to be 4 cubed. And then we'll go ahead and rewrite. Okay, so 3 cubes 27, 4 cubes 20 is 64, so this part's good. So because exponential functions are 1 to 1, we can go ahead and equate the exponents. So x is equal to 3. Alright, got a couple more for you. Let's say we have 8x squared minus 96 equals 64 to the 2x. They do not have like bases, so we're going to have to do a little bit of thinking about this one. Lucky for us, 64 is 8 squared, so we can go ahead and replace the 64 with an 8 squared, and then it has an exponent of 2x also, so we need to make sure that's included there too. Now, one of our exponent properties is if I have an exponent raised to an exponent, I multiply. So 2 times 2x is going to be 4x. Okay. Now the bases are the same, so we can go ahead and equate the exponents. And you're not allowed to forget anything in this math class until at least the end of the class, and if you're moving on, you still can't forget anything. This is a quadratic, and we solve quadratics most of the time by setting it equal to 0 and hoping that it factors. So we're going to subtract 4x from both sides. Okay, and what I'm looking for are factors of negative 96 that have a sum of negative 4. So it might take you a little bit of time, but if we try 12 and 8, 8 times 10 is 80, 8 times 2 is 16, so 80 plus 16 gives me 96. So 12 and 8, and we need a negative 12. Because the coefficient here is 1, we can go ahead and just use what we got from our diamond. Okay, so we actually did get 2 answers. So what might have happened is if we actually graph these two things, you know, maybe one looks like this, and then maybe the other one grows a little bit slower, something along those lines, so you have a intersection there and an intersection there. So it's still 1 to 1, but we do have 2 places where it might intersect. Okay, so 2 more. Alright, 12 to the x equals 121. Don't have the same bases. 121 is 11 squared. Okay, still don't have the same bases. One's 12, one's 11. We can try to break 12 down, but we can break it down into 3 times 4, 2 times 6, or 2 times 2 times 3. None of those are close to 11. So we're stuck right here. There's nothing more we can do. We're going to need the inverse of exponentials, which is the logarithms. The logarithms will undo exponents, kind of like division undoes multiplication, addition undoes subtraction. We need logarithms to undo the exponents. So we're stuck here. There's nothing we can do at this point in time. So we're stuck. We need logs. We'll do one more type of problem that you might encounter in this section. So if we're given g of x equals 3 to the x plus 4, this is an exponential function with a base of 3. 3 is positive, which it needs to be, and it's greater than 1, so this is going to be exponential growth. And the plus 4 would be a horizontal shift up 4 units, which would move your horizontal asymptote of y equals 0 up to y equals 4. And there's two types of questions that they might ask. They might say, if x is such and such, find the y. And the other question they might ask you is, if y is such and such, find me the x. So we're going to look at the first question. Find g of negative 1. So what that's saying is if x is negative 1, tell me what the y is. G of negative 1 is the y value. So we're going to replace the x with a negative 1. Okay. Negative exponent means take the reciprocal and then keep that power, the positive version. So this would be 1 over 3 to the first. And add the 4, and we get 4 1/3, or if you want to put it in your calculator, that'd be 4.333333. Okay, this is the easier of the two questions. If x is such and such, find the y. So you just plug that value right in. The second, more tricky one, and you got to pay close attention to the instructions. They're going to say find x. We don't know what x is. So find x when g of x is equal to 31. So they're going to tell me what the y is this time. They say y is 31. They want us to find what the x is. Okay, so y is 31, and that's going to equal to 3x plus 4, and we want to solve for the x. So one guideline for solving exponential equations is you need to isolate the exponential. So we're going to subtract 4 from both sides to isolate the 3 to the x. Alright, now it looks a lot like something we've done before. 27 equals 3 to the x. So I need to somehow trick 27 into looking like a power of 3, and lucky for us, 27 is 3 cubed. Okay, so 3 cubed is equal to 3 to the x. So now we can equate the exponents. So x is equal to 3.